Thank you for watching this video presentation. My name is Daniel Lange and I am pleased to introduce High5 to you, an immersion preserving attention guidance technique in virtual reality, which was developed by my co-authors Tim Claudia Stratmann, Uwe Grünefeld, Professor Susanne Boll and me. VR allows us to have immersive experiences. It is described by Pimentel and Texera as an interactive immersive experience generated by a computer in which immersion is understood as the extent to which the used technology provides a living illusion of reality for the human senses. So with recent advances such as improved tracking, higher screen resolutions and wider fields of view, VR technology has become increasingly immersive. Due to the freedoms that the user has in a VR world, the problem that the user might miss relevant content that is presented to him increases. To solve this problem, many creative and interesting techniques have been developed, which can be roughly divided into three categories. Techniques that rotate the user or the virtual world, techniques that manipulate the environment by saliency changes or blurring of certain areas, and techniques that augment relevant content by artificial effects. However, all these techniques have one thing in common: they affect the user's experience by modifying properties of the presented world, which can have a negative effect on the perceived immersion. In the field of cinematic virtual reality, a fourth category of attention guidance was investigated, which is common in film and theater: diegetic cues. These are visual or acoustic cues that are part of the presented world. Nielsen et al. Investigated if a firefly can be used as a diegetic stimulus to make a plot more comprehensible, and Rothe et al. Investigated moving objects in a CVR environment. They found that moving objects can attract attention even without sounds. However, there is no generic diegetic visual cue that is applicable in a wide range of settings and environments. This inspired us to create a cue that directs attention and can be perceived as part of the world. However, this creates a problem. Since the cue is supposed to make sense in the context of the respective environment, it must have generic properties that allow the cue to be adapted. So it had to be a cue that works in different environments, that is diegetic and does not affect the immersion in a negative way. This gave us the idea to use a visualization based on swarm motion. As you might know, a swarm is a group of individuals that moves as a collective. In nature, different manifestations of such swarms exist, like flocks of birds, schools of fish, or insect swarms. The advantage of swarms as visualization is that swarms exist in nature and they create a constant field of motion, which is a strong cue in peripheral vision. But when we speak about motion, we have to consider that there is a difference in human perception of biological and non-biological motion. Biological motion refers to motion patterns emanating from living organisms. For example, if points of light are glued to the main joints of a person and the person moves when the light is switched off, we are able to recognize a person in it, which is visible on the slide. The literature suggests that biological motion is easier to detect than unstructured non-biological motion, and that biological motion is perceived incredibly fast compared to other types of motion. For this reason, we wanted to find out not only if a swarm-based visualization is suitable for guiding attention, but also if biological motion can be perceived more quickly in VR than non-biological motion. But how do you implement such a swarm? And does the type of motion influence the perception? To answer these questions, we first designed the basic system and defined all the basic parameters that should apply to the swarm and both motion types. Let's take a look at the parameters. First of all, we decided to take a lot of inspiration from bees, as bees appear in swarms and would fit well within any outdoor environment. But how do we get three-dimensional trajectories of flying bees to transfer them into a VR environment? We have researched the literature to see if anyone has already made the effort, but unfortunately we couldn't find any data on bees, but on midges. Sinhuber et al. Tracked midges under laboratory conditions in a glass box and recorded their positions in three-dimensional space with a resolution of 10 milliseconds. We used this dataset to reproduce biological motion in our system. To create the non-biological swarm, we decided to use the flocking algorithm by Reynolds, which despite its simplicity produces some very good results. Then we defined the basic parameters both swarm variants have to share. We decided to use the color yellow since some bee species are yellow and is also the best perceived color in peripheral vision. Our bees consist of a sphere shape with a diameter of 5 millimeters because the average worker bee is about 5 to 7 millimeters in size. In order to find out the right amount of bees and spread for the entire swarm, we conducted a pilot study with 3 people. We chose 10 bees to avoid cluttering the background too much. Derived from the speed at which the recorded midges moved, we found a velocity of 0.35 units per second with a spread of 5 degrees visual angle in each direction works best. Since our technique is inspired by bees, which are living in a beehive and has a spread of 5 degrees in each direction, we call it Hive 5. To avoid further graphical influences, we used a unicolor shader without reflections and switched off shadows for the bees. Without prior knowledge of swarms, the two kinds of motion are visually indistinguishable. We implemented the swarm in Unity and they are looking like this. As you can see, the biological swarm is rather chaotic and the individual midgets are moving without an obvious pattern, while the non-biological motion is a little bit smoother and more uniform. But which of these two types of motion is perceived faster in VR? That is what we wanted to find out with our first study. For this study, we asked, what effect do biological and non-biological swarm motions have on the response times for attention guidance, and in how far does motion in this scene influence these times? In H1, we assumed that the biological motion swarm is perceived faster. In H2, we assumed that additional motion in the scene masks the motion of the non-biological swarm. Now let's take a look at the study design for the first study. We conducted a within subjects controlled laboratory study in VR. We implemented Hive 5 in Unity and used the HTC Vive with an eye tracker to measure the user performance as the time to first fixation, which is the time between the swarm appears and the first eye fixation. To add motion to the scene, we have used two different environments created from Unity assets, an artificial city environment with motion in it and a natural forest environment. In order to create eye movement, we let the user look at a sphere that moves in the field of vision on the path of a lemniscate. After a random time interval of 25 plus minus 5 seconds, the swarm appeared and the participants were instructed to look at the swarm as soon as possible and to press a button. The environments looked like this. In the city environment, the participants stood at a busy road, so that permanent motion was created by passing cars in the field of vision. The forest environment was completely without motion inside of the scene. To carry out the study, we recruited 20 volunteer participants aged between 23 and 60 years with corrected or corrected to normal vision. No participant had any experience with VR. We have measured the influence of motion through the environment on the user with the virtual reality sickness questionnaire and were able to measure that there is an effect because the FORSQ score is lower on the forest setting. As the results show, in the city setting, the swarm with non-biological motion led to a significantly lower time to first fixation than the swarm with biological motion. In the forest setting with less environmental motion, the effect was even stronger. In total, the swarm with non-biological motion led to a significantly lower time to first fixation than the swarm with biological swarm motion averaged over both settings. The response times for swarms with biological motion were slower than for swarms with non-biological motion. Therefore, we cannot accept H1. Furthermore, it is interesting to note that the additional motion in the city environment caused worse reaction times, but only for the non-biological swarm. This could mean that the biological motion cannot be masked by other motion as easily as non-biological motion. So we can accept our hypothesis H2. In a further study, we wanted to find out whether Hive 5 compete against known techniques. So for the second study, we asked which technique guides users' attention the fastest while preserving the perceived immersion in virtual reality. In H3, we assumed that Hive 5 performs best with regards to response time, and in H4, we expect Hive 5 to have the least negative impact on immersion. In our second study, again, we conducted a within subjects control laboratory study in VR using the HTC Vive and an eye tracker. We compared Hive 5 to implementations of arrow, blurring, dead eye, and subtle gaze direction. The study was slightly modified and now consisted of a search task that took place in the virtual forest setting from the first study. An apple tree was filled with apples and one random target apple, which could only be found with the help of the techniques because it had no unique visible features. Otherwise, the study conditions were similar. After the technique was detected by the participant, they pressed the button and the target apple could be selected with a SteamVR laser. We have, among other things, measured the time to first fixation and the perceived presence with the iGroup presence questionnaire to get a feeling for the experienced immersion. Now let's take a look at the implemented techniques. We implemented arrow as a 3-dimensional arrow with a length of 5 degrees visual angle and a yellow color. The tip of the arrow is located directly on the apple and circles around it, while the back of the arrow points in the direction of the participant's gaze. Blurring was implemented as described by Harter et al. And was used in its strongest form, since the background is also permanently blurred by the eye movements. The target was unblurred and placed centrally in an area with a diameter of 5 degrees visual angle. Subtle gaze direction was visually implemented as described by Bailey et al. By placing a 2-dimensional round shape directly on the target. The pixels were each brightened or darkened by 9.5% with a frequency of 10 Hz. Dead eye was implemented as described by Krekhoff et al. By rendering a target on one eye only. High five was used by having the swarm appear close to the target apple and therefore marking it. First we will have a look at the results regarding H3, which technique was perceived faster. Only the perceived stimuli per technique were taken into account. So we found significant results regarding time to first fixation, with arrow and high five being perceived the fastest, with times under 1 second in the median, closely followed by subtle gaze direction and blurring, while dead eye being perceived the slowest. We suspect that the participants' concentration on the sphere, combined with the permanent eye movement and motion within the scene, have made perception more difficult. Although high five was very fast, arrow was perceived minimally faster, which is why we cannot accept hypothesis H3. But let's take a look at the results regarding H4, which technique had a less strong influence on the immersion. The results of the IPQ shows that the participants experienced the highest sense of presence and the highest degree of realism with high five. A large majority of the participants shared the opinion that high five fits best into the environment, which suggests that high five was perceived as a diegetic stimulus. The results of the subjective measures shows that very few people felt distracted by high five, while dead eye and blurring distracted them the most. This means high five allows us to guide attention while maintaining the sense of presence and thus immersion. In contrast to the other techniques, which generating attention through artificial cues, high five fits well into the environment and therefore we can accept our hypothesis H4. So now, let's discuss the results a little further. High five is a technique that must be carefully adapted to the scenario and the environment to preserve immersion, but we are confident that swarm visualization and an abstraction of swarms to particles will open many fields of application. While we have tried to find the most realistic parameters for high five, we think that high five's noticeability can probably be improved by adjusting some parameters like color, speed, and spread of the particles. One can also increase the number of particles and use animated models such as 3D models of bees to maybe increase immersion and saliency. But how transferable are the results to other applications? With cinematic VR or gaming as the main application fields of our technique, there is a high chance of having motion in the scene, and our first study showed two interesting things. First, we saw that additional motion influences the performance of the non-biological swarm, and second, it appears as though the biological motion is less affected by this, and that even with more motion in the background, the perception of the biological swarm stays more or less the same. This could mean that the biological motion could be a good alternative for scenes with a lot of motion. But of course, our technique has limitations as well. As I said, high five is using a visual diegetic stimulus and must be carefully adapted to the context of the used environment. However, this also means that there will be environments in which the method makes no sense. For example, flies in an office environment may make sense, but it is not common for them to be in swarms, and users might feel irritated by a swarm visualization in this context. Also, we can imagine that the swarm motion could have a negative effect on people if they have phobias about animals that move in swarms like some insects. Okay, let's recap. We can conclude that high five results in fastest response times together with arrow and has the smallest negative effect on perceived immersion. Our results suggest that humans immersed into VR can distinguish between biological and non-biological motion. Interesting is that the quality of perceptions of non-biological motion seems to deteriorate when additional non-biological motion takes place in an environment. We think further work could adapt high five to make users aware of targets outside of the field of view, or create alternative applications like multicolored variants, and different motion patterns. We hope you enjoyed the talk. Thank you very much for your attention and stay healthy.